Hello, everyone, and thank you for attending today's webinar, Hyperlux ID, Overcoming iToF Challenges Enabling Precision Depth Sensing for Industrial and Commercial Innovation, presented by onsemi and Fierce Electronics. I'm Rebecca. I'll be your moderator for today. I'd like to introduce our speaker. We're going to be joined today by David Mills, Business Development Manager, Intelligent Sensing Group at onsemi. David, please go ahead.
Rebecca, thank you for that wonderful introduction, and thank you for Fierce Electronics for giving me the opportunity of delivering this webinar today. So let me talk about what I'm going to be talking about today. So let me run through the agenda. So I'm going to talk about 3D sensing and why that's important in various applications. I'm going to talk to you about various 3D sensing techniques that you may or may not be aware of and the advantages and disadvantages of each. And it's important to understand that when we talk about the design challenges of our solutions. I'll then give you some background on iToF. I won't take you through a complete detailed summary, but a background on the important aspects of iToF and how it works. I'm going to talk about some applications and specific use of 3D sensing in those applications. Then I would give one example. So it's going to be one of those application examples to take you through what the need for 3D sensing is and the design challenges for each aspect of that. And then I will introduce our solution. Our solution is Hyperlux ID. And I'll talk about how we can overcome those design challenges that you get with existing iToF. And then I'll have a summary, and as Rebecca says, we'll open up for question and answers at the end. Okay, let's move through here. So, depth sensing overview and operation. So there's a lot in this slide, but this talks about the various 3D sensing methods that can be used for 3D. And why is 3D important? It's all to do with capturing and digitizing three-dimensional shapes. And that's important for many growing applications I'll come on to later. It's the foundation for mapping. It's the foundation for spatial awareness. So it's becoming increasingly important for many markets to have a 3D aspect rather than just a standard visual 2D imaging. So various methods that are used today, 3D's been around for some time, but typically this has been done with triangulation methods. So I'm starting on the right-hand side here. So if you look at passive stereo, this is using two traditional cameras, two traditional RGB cameras, and an ISP, an image signal processor involved. This really, the determination of depth is done by the distance between the cameras and a parallax between the cameras. So a varying level of depth capability and has advantages and disadvantages. So it goes up to normally a few meters. It struggles a little bit beyond that, depending on what type of cameras you have and what the lighting is and what the subject is. But generally, passive stereo is fine. It's simple camera, but it's actually a complex system. It's a large form factor because you do have multiple cameras. It requires very precise alignments because you need to know exactly where those cameras are. And it's also got high processing power. And you've got two lots of information, one going to each camera that you need to determine that 3D image from. So it can become quite complicated. So the speed can be low because of that processing power. The whole system cost can be quite high because of that. So passive stereo has its place, but really, given some new technologies and one I'll introduce you to today, that becomes a little bit more outdated. Also, then you have active stereo, where you can have a near IR enhanced float and shutter sensors with specific illumination drivers with pixels. That becomes a bit more complicated, but has the same complications. It's two cameras. It needs a complex system. It's very hard to calibrate. So really not ideal for most applications. Then you can also then have structured light. All of these are triangulation methods. You can have structured light, where it's basically just interference of a light pattern reflecting off a subject. In this case, it's not two cameras, but it's still a triangulation method where it's sending out a structured light and then has a receive and then measures the distance. And then the depth can be calculated as an inverse of the camera width. So this is really, it's demanding. In that case, it requires complex animation. Processing power isn't quite so complicated for structured light because it is just one send and receive path. but it's still fairly complicated. Let's move over to the left now. So you have direct time of flight. Direct time of flight is just using a single photodiode, effectively a span array, an array of photodiodes, and you're just sending a light pulse and you're measuring the time it takes to reflect. This is excellent for very long distance, excellent for automotive and LiDAR applications. It's really good at that. The resolution is low because it really is just an array of SPADs, silicon function multipliers. Okay for moving objects, but the hardware is simple, processing power is low. Now, the disadvantage of iToF is that you're not getting any shape, you're not getting any volume. So great for those long distances, but you're not getting anything that you need in terms of volume determination and shape, etc. Okay, so let's move on to iToF, so indirect time of flight. I'll explain what that's the operation of that in a moment. But basically, it measures the phase shift between a signal that's going out and a signal that's reflected. Simple as that. So it's basically looking at the phase shift of a modulated signal as it reflects off an object. Now, this can be fairly complicated in terms of sensor, but our implementation does everything on a single sensor. So as you're looking at an iToF implementation, it really keeps it quite simple from the outside because all of the complexity is done on the chip. Excellent for moving objects. So iToF is really, really good for moving objects. Standard iToF today is struggling with some of those moving objects that it needs to freeze a frame, then do a depth distance, then restart again. So standard iToF today does struggle. I'll explain how Hyperlux ID overcomes that challenge. Resolution is high for iToF because it uses an array sensor. A traditional iToF today is using VGA sensors. Our iToF sensor is a 1.2 megapixel, as I'll go on to explain. Simple illumination, complex sensor. Now, you see here that I've crossed out the sensing range. So sensing range typically for standard iToF today is 8 meters, around about 8 meters. It can be probably up to 10 meters. Our Hyperlux ID smart iToF can improve those distances dramatically with moving objects. So I'll explain that. So up to 20 meters outdoors to 30 meters indoors. So I'll explain that in a moment, how that and how that is implemented. Okay, let's go back to some basics here about what indirect time of flight is. So really, as I said earlier, it's measuring the phase shift or the phase difference between illuminated and reflected light. So you're sending out an illuminated continuous wave modulated signal, and then you're measuring the phase shift, as it shows in the middle there, of the received light. Then you calculate the depth distance based on the speed of light and based on that modulation frequency. Because you know the frequency, the speed of light is fixed, you know what that phase shift is, and you can measure that distance accordingly. So that's really all indirect time of flight is. That then gives you a resulting 3D point cloud from that, which I'll go on to explain. Okay, indirect time of flight needs reflectivity of an object. The object reflectivity then determines how good the signal is that's reflected off the object. So the pixel response is a function of the reflectivity of the subject, the distance of the subject, but then ambient light comes into play. And that's the biggest disadvantage of current iToF today, is that ambient light is an enemy to iToF. Because really that's, it can saturate or it can alleviate some of the signal that's coming off the return of the subject. So if you look on the right-hand side here, this is the total pixel response. You need to deduct that ambient light. So you need to reduce that ambient light as much as possible in order to get the real response from that subject. I'll explain that in a moment, why that's important. Then the iToF theory of calculation, you're doing phase shift. You need 4 images. So you need 4 phases, 0 degrees, 90 degrees, 180 degrees, 270 degrees. So you get 4 phase shifts in order to generate a depth. Okay, and I'll explain why that's how that works and why that's important. So hopefully that gives you a background into how indirect time of flight works. Okay, so now let's talk about some applications and some of the design challenges that are around at the moment. So huge amount of applications here. So you've got smart buildings and cities, industrial automation. I'm going to focus an example on industrial your problem's going to come from. But there's many other applications where 3D depth sensing is required. So security, intelligent transportation systems is where depth is required. It's got cars, it's got people that are moving, objects that are moving, depth is required. Smart home, many different reasons why in the smart home, whether it be from smart home goods or whether it be from AR, VR, headsets, lots of different things and needs for depth. Video collaboration is another one. So video conferencing, where you need to determine the distance of the person from the lens or the distance of the subject, and you might want to put in a false background, or you might want to determine what the background is compared to the foreground image. So depth becomes very important for video collaboration. Future retail as well. So that's another application there. Future retail for robots that are moving around and doing assessment of stock, for instance. Scanning engines as well. So scanning engines today is all typically 2D, but knowing where the object is can determine exactly how to put the focus in for the scanner. You can have lots of other things that I'm going to talk about in the factory floor. Why sort of for scanning at factory applications that depth is important. Access control is another application, great application for iToF and depth. So if you imagine somebody wanting to access with a face, wanting to authenticate with face, your face is in 3D, my face is in 3D, I hope it is. It's not a picture. So if you try and spoof with a picture, that becomes a 2D image. You need that depth in order to authenticate the face. So iToF is a great way of doing that, determining that depth. So machine vision has always needed depth. So today, almost everything is done in 2D, but having that determination of depth in machine vision applications is very important for factory inspection and machine vision applications. Factory robots. So you've got robots that are going around needing to map, needing to make sure they don't collide with things. That becomes really important. Depth is needed there. AGVs and AMRs, guided vehicles and mobile robots also need that depth information in order to navigate and for the simultaneous location and mapping techniques. But logistics is actually a very good application for iToF. So logistics applications where boxes are flowing on conveyor belts, where you need to determine the depth of the object, where the object is, and the volume of that object, as well as the details of that object. And inventory management, in a similar way to logistics, you need to determine the depth of the goods and things that are moving. So all of these are growing applications, emerging applications, and depth is critical to all of these. So let's move on to a specific example here. So I mentioned I was going to give an example of a smart factory. So as I mentioned earlier, here you see a nice picture that's showing a robotic arm. It's showing a factory inspection line, and it's showing robots, so mobile robots and guided vehicles that are moving things about, and vehicle loading. So for a robotic arm, depth is needed to grab objects. So the vertical direction is needed. So as you've got a robot arm that's picking something up and then needs to do an AI determination of that depth, that is needed. iToF is excellent for that and the type of depth that we're capable of getting with Hyperlux. The inspection line, depth is needed to find defects where 2D visible, it can be used on inspection lines, but 2D visible might not be sufficient for finding that depth and having that depth calculation on the inspection line. And as I mentioned earlier, the AMRs and AGVs, depth is required for mapping, navigation, collision avoidance, and also for safety as well, because humans are around. So you also make sure there's the safety aspects to that as well. Then when you get to vehicle loading, this is where you need to start applying intelligence. So depth is needed for measuring the dimensions of the objects, dimensions of and volume of those objects, and does the optimized loading. So you can order boxes in certain ways in order for optimized loading. They would love to have depth to do that today, but it's quite costly to do it, and it hasn't been great to do it. So there's many design challenges that mean that iToF is very rarely used in these. So then we're getting down to these design challenges, and how can onsemi solve? We certainly can with Hyperlux ID. So motion artifacts. So in today's iToF, there's many motion artifacts, and I'll explain how you can get blurring with today's iToF and how we overcome that. Accuracy and resolution, I'll explain how we overcome the resolution aspect with our 1.2 megapixel global shutter sensor and our excellent accuracy and how we're able to get there. Long distance range, back to my example that I was showing you on that inspection line where you've got varying distances from something which is close up to something which is long distance. So traditional iToF today, as I mentioned in my introduction, can go out to a few meters, perhaps up to 5, 6, 7, 8 meters. We have shown that you can get to accurate distances outdoors up to 20 meters, which is leading the industry in terms of iToF, in terms of depth calculation. Indoors, we can get up to 30 meters. So really, for rooms, most rooms are 30 meters or smaller. So it's absolutely ideal for that. System cost and space. This becomes really, really important when you're designing a system. You need to make sure you're keeping that small footprint because of the say a robot arm where you've got limited space in order to have the depth sensor. You need to have low system cost, and I'll explain how Hyperlux ID, because of our embedded depth calculation, enables that low system cost. So I'm going to explain now how the new Hyperlux ID that we just introduced overcomes all of these design challenges. Okay, so solving the design challenges with Hyperlux ID. Let's start with motion artifacts. So I mentioned about the blurring, and standard iToF has this blurring. So standard iToF today doesn't have any in-pixel memory. So if you recall back to what I said in the introduction about the way iToF works and the need to have these 4 phases in order to calculate the depth, standard iToF today, because it doesn't have in-pixel memory, needs to do an exposure and readout, exposure and readout, and needs to do that consecutively for the 4 phases. So in this case, we're showing dual frequency with 4 phases of each. So there's 8 readouts and 8 exposures. There's a huge time lag between the first exposure and that last readout. And it's that exposure period that affects motion. So if you've got motion, you're not doing a full deterministic realization of where that object is. So in that diagram on the left here, you're seeing someone throw that ball up, and you're seeing some blurring in there. So what does Hyperlux ID do to overcome that? So Hyperlux ID stores all of the 4-phase information in the pixel. So this shortens the time between the phases. So basically, you can do all 4 exposures for each frequency consecutively. So you can have those 4 phases that I mentioned, 0 degrees, 90 degrees, 180 degrees, 270 degrees, and you can do that for both frequencies and then do all of the readout because we have this in-pixel memory that enables the readout to all happen after the exposure. So why is this important? It enables fast-moving object capture. So conveyor belts, robot arms, surveillance, all these applications that have fast-moving objects, this becomes really important in making sure that you have this accurate, less blur of objects in recognition. Things like gesture control as well. Gesture is very important. So for applications where gesture is needed, a lot of blurring, a lot of fast movements. And in wearables, there's lots of fast movements. So this is overcoming the challenge with Hyperlux ID. So this is an example of against a competitor. So I won't name who the competitor is, but there's not that many iToF sensors out there. So you can pretty much guess what who the competitor is. This isn't actually played, this should play. This is a video showing a rotation of blocks of various depths. And you can see with our competitor, you can't quite see it, but if the video is playing, you'll be able to see that there's a blurring effect that our competitors have compared to the highly accurate depth determination of Hyperlux ID. Okay, I've also talked about accuracy and high resolution. Hyperlux ID has precise sensing results. It has a high sensitivity global shutter BSI, backside illuminated global shutter pixel. So backside illuminated, very highly sensitive, particularly in the near IR range. So obviously we're using pixels that are in the near IR range. In this case, 940 nanometer lasers So you really need to have that high sensitivity at that wavelength. So at 940 nanometers for Hyperlux ID, we have a 43% QE compared to existing iToF, which is much less than 30%. That's really important for accuracy. So the depth jitter that we can get to is less than 0.5% at 0 to 5 meters. So 0 to 5 meters depth, we can have a depth jitter of less than 0.5%. So think about that in terms of millimeter determination with accuracy of depth over a 4 to 5 meter range, which is typical in warehousing or factory type of applications. And also, this is a high resolution sensor. This is a 1.2 megapixel global shutter sensor. Most sensors out there today are VGA resolution. Now, when we get out to longer depths, we do binning, and we then get down to that VGA resolution. So we're improving the pixel size and the overall sensitivity by going down to VGA resolution. They're doing binning, and then it becomes an effectively larger pixel and has that ability to go out to longer distances with that bin. So high depth accuracy and high resolution. So that's really important. So this is showing an example. This is what we use for our demonstrations at our trade events, actually. This is a block that has various steps on it. And you can see the depths of the steps. So here is a complete 11 millimeter high. Bottom block is 2 millimeters, and each block in between is 1 millimeters. So with the camera positioned at 75 centimeters over that block, don't forget, this is moving fast as well. This is all about capturing that depth resolution while it's moving. This is not stopping or starting it. This is doing it all while it's moving. Because of that, as I mentioned earlier, having that in-pixel memory, and onboard depth calculation, global shutter, all those things working together enables this to work in fast motion. So in this case, this is working with 4 pixels, the exposure time of 250 milliseconds. So this, you can clearly see that we are quite easily determining that 1 millimeter depth. This is the depth map. This is a false color depth map. And a 3D solid model that also comes out of this. So you're getting a lot of information that's coming out of the sensor, which you get out of a standard iToF sensor. Okay, so how do we get to this long depth distance? As I mentioned in my introduction, ambient light is really the enemy to iToF because you're looking at a reflected signal. So you want to reduce that ambient light as much as possible. So the way iToF works, as I mentioned, continuous wave modulation. So you need to keep that laser power low and keep that. A traditional iToF would use a pretty low peak power and a continuous wave modulation. That works fine. That really does start to struggle when you get high ambient light. So how do you overcome that? You can do pulsing. You then increase that, the laser power, you increase that up to 30 watts, and then you pulse it. Because it's a global shutter sensor, you can pulse, you know exactly when you can do a deterministic when the receiver is going to come. So you just open that global shutter sensor just as you do the send and receive. So all of the ambient light in between is rejected. So then you look at the bottom here, Smart iToF. This is a unique implementation. It's patented by onsemi. This is a combination of the advantages of both of those. So you're getting pulsed and continuous wave together. So you're getting the advantages of having the pulsing, and you're getting that continuous wave, which is essential for that phase shift. So if you look here, you can keep that high peak power, and you can do a space in between. So in this case, this is showing an example of a 10 megahertz space in between. And this is really reducing that ambient light that's in there. This enables less aliasing and enables a very long distance. So this is up to 10 times the distance of standard iToF because of the increased peak power and the ability to be able to reduce the ambient light. So if you're looking at this here, other iToF, up to a few meters, our smart iToF implementation, which is Hyperlux ID with the smart iToF or hybrid mode. We call this a hybrid mode being phased and pulsed together, you can get to very long distances. As I mentioned earlier, iToF, you can get out to very long distances, but doesn't have that volume determination. Okay, let's move on. So that's accuracy and depth distance. So depth distance here, this is showing some examples of depth distance and showing what you get out of the sensor. So this is a false color map. So the false color map is really a color is applied to a particular depth. So the sensor gives you it looks like a color image, but it's actually a false color image where the colors represent different depths. In this case, we're showing an outdoor scene. This is 70 kilolux. That's a lot of light in 20-meter range. So a lot of ambient light here, and you can get full deterministic distance at 20 meters. Indoors, you've got less light. So indoor starts to become easier because you've got less ambient light. Here we're showing 20-meter range, and here we're showing a 30-meter range. So this is a simple 30-meter range using that hybrid smart iToF implementation in order to get very long distance. This is talking about the ambient light rejection effect and showing some examples of where you've got direct sunlight. This is an automotive application. Actually, I didn't mention automotive at the start there when I was talking about industrial and commercial applications. iToF is also applicable for automotive, so for driver occupancy and for driver monitoring applications, it's ideal. So here you're looking at a driver, and actually this driver here is our chief designer, who's based in Israel. So in Israel, it's sunny pretty much most of the time, so it's pretty easy to do these examples. Sunlight effect here, sunlight coming onto the side window, sunlight onto dirt. So with our sensor and what I talked about earlier about having an ambient light rejection, which is the nanometer iToF, you're really taking away with some exposures, you're taking away that ambient light. And actually, and while I'm here talking about this amplitude image looks like a standard monochrome image. This is something else you can get out of Hyperlux ID because it's a standard global shutter sensor, 1.2 megapixel. You can get an amplitude image, which is an equivalent monochrome image from the sensor. So you're getting a standard monochrome image, and you're also getting all this other depth map and depth point cloud, confidence, and phase out from the sensor as well. So you can see here, depth output is not affected by the sunlight because of those methods that I outlined earlier. So low system cost and small size. Why is that becoming important? So if you are looking at a system today, you're looking at other iToF, you need to have frame memory. Now, I mentioned earlier that we have in-pixel memory, so we don't need to have that external frame memory. The frame memory is an additional cost, it's an additional size, and it's also additional latency. So having this iToF sensor needing the external frame memory is not ideal. You also need to have an external MCU or an external calculation, an FPGA for that depth calculation. And then you need to send that out to the system FPGA or ISP. Hyperlux ID has all of that depth calculation on the chip and has the in-pixel memory. So there's no need for a frame memory, so there's no need for that external memory. Has that low latency that I mentioned earlier, and combining that with the global shutter keeps that latency very low, and has all the depth processing on board. So less external devices, so a relaxed interface speed, and low computational power. So really you're keeping that system cost very low, you're keeping the size small, and you're keeping that, and overall you're keeping that latency very small as well. So there's no other iToF solution that offers what we're offering with Hyperlux ID of having that depth process availability, having that in-pixel memory. So there's so many advantages of having of Hyperlux ID, which I'll outline and summarize in a moment. So integrated depth process. So the things really to take away here, it's keeping that system cost low. So when you look at the price of the sensor, which is reasonable for this global shutter offering, it's also keeping that system cost low and simple. even though computational requirement on the sensor, as I mentioned right at the start, is actually quite complicated from the outside. It's not. Okay, so let's go through these again. I would like to go through all of these challenges and how we overcome them again, and give you some more overview of what the sensor is. So this is a 1.2 megapixel sensor. It's a 1/3 optical format. So standard lenses can be used with this, and 1/3 lenses are pretty much available. It's a 3.5 micron pixel BSI sensor, so a highly sensitive BSI global shutter sensor, bins to an effective 7 micron pixel when you get to binning and VGA. The frame rate is 60 frames per second, and you can get up to 100 frames per second when you do binning with on-chip depth calculation. So this far surpasses anything that's out there in the market today. There's nothing out there in the market that can do full resolution, 1.2 megapixel or high frame rate VGA resolution depth with motion today. Has a excellent modulation frequency and a very high modulation frequency up to 200 megahertz. So I'll summarize again: low motion artifacts enabled by unique integration and readout structure, along with that global shutter and along with that on-chip storage. So all of those things are working together. That smart iToF, that global shutter, in-pixel memory, and on-pixel depth calculation. High resolution and accuracy. We know that resolution is important. Accuracy is also very important. So enabled by this 1.2 megapixel global shutter sensor. Low system cost and size. Depth is all done on board. As you see down below here, this Hyperlux ID has this on-chip storage and this ability for this intermittent modulation, which is smart iToF, by the way, all on the chip. So from the outside, it's all done for you. So low cost, low small system, and small sockets. Long depth distance, so keeping that accuracy over distance. And actually, we can get, because of the way we do the determination of depth, we can also get down to very short distances as well. So you can have, we've demonstrated just a few inches or a few centimeters, so up down to about 5 centimeters, you can get excellent accuracy and distance as well. Also, this uses a standard development environment. So if you want to evaluate this sensor, you can use a standard hardware that we use for all of our Hyperlux sensors. So we have a family of Hyperlux sensors, Hyperlux LP, Hyperlux LH, Hyperlux SG, all have headboards on the sensors, and our legacy sensors all had headboards with a standard baseboard that plugs through the USB into the computer. The development environment for that is called DevWare. So DevWare is renowned in the industry as the most flexible application software for pixel evaluation. iToF Hyperlux ID also works in a standard DevWare environment. So you can do exact pixel evaluation, and you can get the depth map, point cloud, that confidence, all available through that DevWare interface. So applications, we talked about machine vision, factory automation, metrology as well. We haven't talked about metrology and that need for measurement in a machine vision application. Metrology is very important. Logistics is important. I didn't mention healthcare either. That's at the start. Healthcare is also a lead application for iToF as well. So whether that's surgical CD is required for surgical assistance in place, and making sure that the body movement isn't impacting anything to do with that healthcare. So healthcare is one I didn't mention, but that's also an application that's very important. Robotics, AGV, SLAM, drones, I mentioned all of these. Drones I didn't quite mention, but drones take a number of guises, whether it's standard drones for things like smart agriculture or surveillance, but also for smart retail as well, where depth is required. And these smart retail drones, depth becomes very important for that as well. Accessing and area control, safety, biometrics, really there's so many different applications where iToF can be used, but isn't used today because of all these design challenges that I mentioned earlier, that we are overcoming with our Hyperlux ID architecture. Consumer is also another application for iToF, so whether gaming controllers, AR, VR, I mentioned gesture recognition, robotic vacuum cleaners, humanoid robots, all require depth. So let's just go through it as a summary here and how we're overcoming. I think I've said this many times, but I'm going to keep reminding you of the advantages of Hyperlux ID, standard iToF, and how we're overcoming those existing iToF challenges with Hyperlux ID. So motion artifacts. You don't want motion artifacts when you're doing depth. The solution, onboard memory, real-time processing. Accuracy and resolution. The solution, higher resolution, global shutter sensor in our case. Accuracy at very short distances as well. So accuracy both at long distance and short distance. Long distance range, especially outdoors. So, and again, with movement, it's having this long distance range with movement by having this smart iToF phased and pulsed send and receive. If you remember that smart iToF, that hybrid of continuous wave and pulsing together, and that high ambient light rejection. And that is key to getting that long distance. So all of these working in unison to give you that ambient light rejection. And as I've mentioned many times, this built-in depth processing to enable reduced system cost and reduced space. So the offering that onsemi has, I haven't mentioned any part numbers here, but I'll now mention part numbers. So Hyperlux ID consists of a family of two devices. One is called the AF0130, and the other one is called the AF0131. So the AF0130 has this built-in depth processing. Most people will want to use that onboard depth processing. But there are situations where customers will want to use their own algorithms and want to use their own proven depth processing that they have. So the AF0131 has the same, everything exactly the same as the 0130, but doesn't have that processing built into it. So that's an offer that we can also enable our customers with. As well as the hardware that we can enable for this, people are going to ask if we can have a module to solve the system challenge, building a module into the market as well. As onsemi, we're not going to be selling modules. We enable modules into a market with reference modules. We currently have Hyperlux LP, LH, and SG. We have Premier reference image sensor modules, which are reference modules. We will have a similar thing for Hyperlux ID. So we will have a reference module, which will be just a standard iToF sensor with a lens, with pixels and laser drivers on board. So the sensor itself has the pixel control, then sends out to the laser controllers and the module that files as a session. So we can enable a whole solution for a customer, whether that's evaluating, we can enable a low cost, high accurate solution, and we can also enable a reference module for building that solution that will come out soon. Okay, so this is Hyperlux ID. So hopefully ID stands for indirect depth. I said that at the start. So the Hyperlux ID, and you want that to be true, iToF indirect depth. So it's iToF depth or indirect depth. It goes hand in hand with our other B family for low power from 5 megapixel, 20 megapixel. We have a Hyperlux LH family, low power, high dynamic range, up to 12 megapixel. And we also then have 2 megapixel, 12 megapixel, and we have Hyperlux SG, which is small global shutter, which is VGA resolution, 2 megapixels. So that's really, this is another addition to that Hyperlux family. So hopefully you can look at a whole Hyperlux family and what was covered. So I think that that concludes what I am presenting today.